Kia ora and welcome back to the 2012 paper. In this video we're going to look through question 2. This question's quite reasonable as well. Part B has the potential for a bit of a misconception, which we'll cover when we get there. And part C was actually a question in Skull Calc which required you to write. And I haven't seen an exam since 2012 that's had an example of a question like that. So maybe they tried it out and it didn't work. Alrighty, question 2a. I've got an equation x to the n is tan ny. And we're told that n is a constant, and we need to find dy dx. This is stock standard implicit differentiation. You could, if you wanted to, make x the subject of this. So you could write tan of n to the y to the power of 1 over n, then find dx dy and flip it upside down. But not all equations can be rearranged. Sometimes it's not possible to make one of the variables the subject of the equation. So it's useful that you understand how to do implicit differentiation. Okay, so if we want to find dy dx, we just differentiate both sides as they are. X to the n, n times x to the n minus 1, because the power is a constant, it works. And then the right hand side, tan differentiates to sec squared. There's an n in the middle, n times y, so we get n multiplied by sec squared ny. But we also get a dy dx. Okay, and the reason why we get the dy dx there is we actually wanted to diff this. We're diffing it with respect to x. And what you need to realize is y is some function of x. And when we diff something like that, where it's a function of x in the inside, we use the chain rule. Tan is the outer function, that diffs to sec squared. And then we multiply by the inner function's derivative, which is n times f dash of x. And then, of course, f dash of x is dy dx. So that's an implicit differentiation is just the chain rule. And you know how to differentiate using the chain rule because it's achieved in NCA level 3. You just don't see, you won't see expressions or equations where the dependent variable y is in the expression at level 3, but it's quite common in scholarship. Okay, now we want dy dx to be the subject of that. There's an n on both sides, which we can cancel. And then we got dy dx is equal to x to the n minus 1 over sec squared of ny. Now the question asks us to write it as a function of x, and that means we need to go back to the original expression and replace the tan ny part, or the sec squared ny in our expression. So we know that x to the n is equal to tan of ny. There's a couple of ways of going about this. One way to do it would be to know your trig identities really well. And if I was to square this, I get x to the 2n, x to the n times x to the n. And this right hand side would become tan squared of ny. When we multiply tan by itself, we get tan squared. And then tan squared, well, there's a formula on the identity formula sheet that says sec squared minus tan squared equals 1, which means that sec squared ny minus 1 would be equivalent to that. Now we can rearrange this equation. That means that sec squared of ny is equal to x to the 2n plus 1, and then that can replace the sec squared ny in our equation. So that's number one. If you know your trig identities and you know how sec squared and tan squared relate, then that's our expression that we wanted. Your other alternative in thinking about this is whenever you've got a trig expression, you can draw a triangle. And in this case, if we think of tan being the opposite over the adjacent, we can write x to the n as x to the n divided by 1. the opposite side of a right angle triangle where the angle is ny, the opposite side is x to the n and the adjacent side is 1. Now, to find sec squared, sec is the reciprocal of cosine. So sec ny is 1 over cosine. So sec squared will be 1 over cosine squared. And then to get cosine, we need to find the hypotenuse of this triangle. We use Pythagoras. 1 plus x to the 2n square rooted. A squared plus b squared square rooted. We want the reciprocal of cosine, and we want to square it. So the reciprocal of cosine is hypotenuse over adjacent, which is 1 plus x to the 2n square rooted, but then we're squaring. And again, 1 plus x to the 2n is what we ended up with in the denominator. So that's another way of thinking about it, that when you've got one trig ratio, you've got all of the other trig ratios, and they just relate by a right angle triangle. Okay, part B. We have a family of ellipses. Family just means that there are constants involved. So all the ellipses are similar in some way, right? They're all of this format, but B, C, and R are going to determine the shape of them. They're all centered at the origin. So they're all a family. They're all like similar, but they're kind of different in their shape, like any normal family, I guess. Find an expression for dy dx, and hence find an equation in the form y equals f of x for the family of curves that always intersect at right angles. Okay, this is another one for implicit differentiation because the equation's not written as y equals. We could rearrange it, but it's tedious. Might as well just differentiate as is. So bx squared plus cy squared equals r squared. If I wanted to find the gradient at any point on the ellipse, I would need to differentiate. The derivative of cy squared with respect to x, we still diff it like normal, but then we put the dy dx factor in, with it. And be careful here, r squared doesn't differentiate to 2r, because r is a constant, it diffs to 0. Then we rearrange that. Minus 2bx all over 2cy minus bx over cy. That's the gradient function of the ellipse. So what have we got here? Nope. Something like that. And we've just found an equation that gives us the slope there. And we want a line that comes in at right angles. The misconception is that we're not actually looking for the equation of a line. Yes, when we zoom in on the intersection point where the tangent meets the ellipse, we'll have a curve that's coming in to meet at right angles, which will look like a line when we zoom in on it. But it's not. What we need to realize is that the family of curves that meet orthogonally, this is a fancy word for at right angles, will have a gradient function that's cy over bx, the negative reciprocal. Just like when you find the gradient of a normal, it's the negative reciprocal of the gradient of a tangent. We took our gradient function up here, you flip it round and change its sign. And now you have to realize it's actually a differential equation that we're trying to solve. So we need to anti-diff both sides. Before we do that, we separate the variables. I'm going to take the b up the top left and the y down the bottom left. And the c can stay the top right and the x can stay there, and we'll get a dx. You can do it in other ways, but that just looks nice. B ln absolute value of y equals c ln absolute value of x plus some new constant. We need to have a constant there somewhere. The convention actually, when you've got logs involved, the convention is to make your constant a log constant. So maybe something like ln a. using A because it's a letter of the alphabet that hasn't been used yet. And the reason why that's useful is because we can use log properties now. Actually, no, we'll use the first log property I'll use is the power rule. And take the B up the top and the C up the top. Why am I putting the C on the inside? And then the other log property we can use is that 2 logs added is the log of the product of those things. So we can sandwich the A inside the absolute value symbol there. And now we can get rid of the logs on both sides by taking e to the power on both sides, which we couldn't do at this point. We can't just cross the logs off. We can only do it when there's 1 on either side. So our equation that we want, y to the b absolute value equals ax to the c absolute value. If you want to get rid of those absolute values, all you need to do is write plus or minus in front of your solution to counter for the fact that it could be a positive or a negative. But a is a constant, so the constant could just be negative. In other words, just use a different letter, and they're our equations. I think it did ask us to make y the subject of it. Yep. Unfortunately, we can with this. It's quite a simple equation to do that. We just need to power it by 1 over b. Okay. X to the c to the power of 1 over b, the bth root. It's kind of sounds like beetroot. And there's another constant. Oh gosh, another letter of the alphabet we haven't used yet. M for my name. X to the c over b. There we go. Now I'm just going to have a quick look at GeoGebra and to show you that these, it's pretty obvious that these things aren't straight lines because c over b isn't necessarily 1, but let's have a look at what we've just made. Okay, the first thing we had was an ellipse. It's going to take a little while to type in. Okay, there's our ellipse. We can play around with the B, C, and R and look at the different members of the family. And then we've got our new equation, which apparently always meets at right angles. Alrighty there. Pretty strange function. Kind of looks like a flat parabola. At the moment it's a power 4 equation because B is 0.1 and C is 0.4, but we can play around with that. And it looks different. Oh, look at that. That's not an ellipse because I've made C negative. To be an ellipse, it need A and B and C need to both be positive. But it's always intersecting at right angles. No matter what the value of M is. Kind of cool. Alrighty. Did it say family of ellipses? Oh yeah, it did, because it said B and C are constants, but it should have actually said that B and C are both the same sign. Otherwise it would be a hyperbola. Alrighty, part C, this strange question that involved us to write a bit. Models of exponential growth and decay arise in many diverse fields. Use calculus to explain why the simple equation models such a wide range of real-world solutions. So if you've done integration, you'll know that this equation appears over and over again. If you're doing NCA level 3, you need to make sure you show all your working to derive this equation every time, even if you know what the answer is going to be. And it's the solution to the differential equation where the rate of change of a quantity, in this case A, is proportional to the amount of that quantity at a particular point in time. So if A is larger, then the rate that A is changing is larger. If A is small, then the rate that A changes is small. Inversely proportional would be K divided by A, whereas if one goes up, the other goes down. If A increases, the rate drops, but this is a proportional one. So if we separate the variables, as is common practice for this, we have to put the integration, even though we know what the answer is going to look like. Alternatively, you could just diff the solution that they gave. Log of the absolute value of A. Usually A is positive if we're talking about the number of people that have a particular disease, or the amount of bacteria, or the amount of money in a bank that's getting compound interest. Then the value of the variable A there would be positive, so we can drop the absolute value symbols. When we anti-diff the K, we get K times T, and then we get an integration constant plus C. Take the E to the power of both sides. I'm just going to get rid of the absolute value symbols. If A is greater than 0, A equals E to the KT plus C, and that's the same as E to the KT multiplied by E to the C, and common practice is to write that E to the C constant as A naught, where A naught is the initial value of A, i.e. when T is equal to 0 is what I mean there. So the initial money that you put into the bank. And we're assuming continuous compound interest or continuous growth, not discrete. So like, for example, disease spreading. The number of people that are getting a disease is going to be essentially continuous. It's going to increase through time, not in jumps. But if you were just visiting certain people and it was in a small community, then you'll get jumps in your number of people that have it. You'll get, it might start with 1, then it'll go to 2, then maybe 4, then 8. It's going to jump, not be continuous spread. In a bank account, you get interest applied at the end of each month. There's only 12 months in a year, so it's not perfectly continuous growth. Okay, and in terms of what do we need to write here? The solution A naught E to the KT of the DE, of this DE here, when the rate of growth, not rate of growth, rate of change is a better way of saying it, when the rate of change is proportional to the amount. Now it's got some limitations. One of the limitations is easy to explain in terms of epidemics. As we saw with all the COVID cases, initially your number of people that have, maybe N could be the number of people that have a disease, T's time. Initially it might approximate exponential growth, but then it gets to a point where there's a limit to the number of people in the population when everyone's got it, and we're assuming no reinfections and all that sort of stuff. You end up getting something that tends off to the population. So that's called logistic growth. So like this model here only approximates growth initially when it's exponential growth. It also suggests that if, for example, you have some medicine and you have some sort of dosage, and it might drop off in your bloodstream, it never gets towards 0. It tends towards 0, but it never gets to 0. And that again is a bit of a limitation, because that's kind of a bit strange. It doesn't really work for the context. If you have medicine, eventually there'll be none in your bloodstream. So that's another limitation, is that it has an asymptote. And if you discussed some of that in your answer, you would get the full marks. Catch you in video 3.